Good morning to everyone. I'm Andrea Revolti from the University of Bolzano, and today I present my paper, Empirical Validation of BIM-to-Digital Twin Transformation for Smart Mobile Factories, a Case Study. Please note that it will be a very empirical and practical presentation rather than a theoretical one, so considering the applied nature of the topics. Okay. This is the agenda for today. I will introduce the Smart Mobile Factories concept and the motivation behind the research. Then I will explain the BIM-to-Digital Twin Transformation for our use cases that is called Field Lab in Zurich. After that, I will describe the modeling steps and sensor connectivity and the real-time data integration. And finally, I will summarize the objective that we achieved, the current limitation of this prototype, and outline the future development of the research. Okay, the Smart Mobile Factory project is a project that tries to address the limitation of a traditional centralized prefabrication facility, which often suffer from long lead times, large batch size, and limited flexibility. In contrast, the smart mobile factories are designed to be mobile, digitalized, and sustainable, allowing a fast setup and dismantling timing, so we can recreate and build the factory every time in 44 hours, following the head of the construction site. The use case is the Hyperloop project of Eurotube, that is the European version of Hyperloop idea of Elon Musk, but in this case is made with concrete and not steel. I would like to clarify that the shape, all the material, the possibility of reassembly, and also the life cycle assessment has been object of our research paper, in which obviously I was involved. In particular, we tested the different layout, materials, dimension of the factories, and also the working area together also with the Eurotube Foundation that explain us how they can build these pieces of pipes and then assemble it all together and then put on the construction site. Instead, at this time, I will focus especially on the BIM-to-Digital transformation and the empirical validation with the field lab. The idea is to start with a BIM model that is built with a specific piece set that have all the requirements that we need to pass all the information in the Unity environment to build a framework that can be working as a digital twin of the factories, in which we have possibility to have decision automation, predictive simulation, also machine learning, data analytics, real-time data aggregation, and asset information storage and management. And then we can move on in the future with the digital twin solution to be descriptive, informative, predictive, prescriptive, and transformative, or of the normal way of working inside the factory, and also moving on the extended reality to use the digital twin on site inside the factory. The use cases is the field lab. This is an old military airport in Dubendorf, that is a small town nearby Zurich, that will be object of future restoration with a lot of building that will be of the University of ETH of Zurich, and then we have a small area that we can use for the testing of the Hyperloop project. This is the area that the municipality gave us to test the construction of the pipe and the factory, and the building of the pipe is already started, so this is me on the construction site of the pipe. The available area is long and narrow, and is characterized by a multiple access road and the internal pathway. At the same time, we have very strict lateral boundaries, limits, imposed by the municipality, as well the maximum height of the building that we have to respect. This condition required careful planning in terms of factory layout, container positioning, and structure dimension, balancing production needs and logical and regulatory requirements of the municipality. In this case, we use the E form of the factory. If you read the other paper, we have different forms that we can use. In this case, we have to use the E shape. And there is that you can see the area, the covered area with the tent, because the configuration that we use, because it's the most useful for reassembly and also the life cycle assessment, is to use a pneumatic tent that is installed on the container that can be a sort of pillar of our structure. And in this case, we use the E-form of the factories. Inside we have the storage area, the casting area that is built to be used with two molds, because they created the European Eurotube Foundation create a sort of mold to create this part of the pipes, and this already arrived in May 2025. We have the curing and the drying area inside the factories. Then we have the assembly and the pretensioning area, in which all the pieces of the ring are built together and then attached together. And then we have the sealing area, in which with a spray they make the void inside, because the train has to move without air inside the pipes. Then we have, after the first layout proposal, we work closely with Eurotube Foundation to reduce the economic and environmental cost. So we reduce the tent, keeping on the curing area and the sealing area that has to be connected and very protected by the weather and the external condition of the world, because there is more let me say precise, and maybe we can make some error inside on this type of working area. So we have some improvement. This evolution of the central tent makes it possible to optimize the surface area for activities that always need protection from the element. And we can also use this tent to place the sensor, we can see later, and have the real-time data that we can read inside the digital twin of the factory. The other improvement is to have a mobile pneumatic tent, very, very small, and we can optimize the sealing activities, because we can move the tent, because it's on pneumatic, in the specific pipe where making the sealing activities with the spray. All the element of the BIM model was characterized by a specific preset parameters implemented according to the Smart Building Council standard. So the idea is to have a standard in which we cannot lose information about the asset and also the sensor that we can put inside the factories, and we then pass the model into Unity, ensuring all that relevant attributes such as dimension, material, and also sensor connectivities remain accessible to be used as a digital twin model. We have two different types of digital twin that we can provide. One is a building scale, in which we have data from the construction site, construction environmental data, and the logistic. And then we can move on a specific and vertical digital twin inside the bigger digital twin of the environment of the factories, focusing on the concrete mixing data, component alignment, and the pipe sealing data. In our case, we tested IoT integration, in which we developed and tested the first more or less protocol between the real sensor and the mobile factory in the digital model in Unity. This protocol allows real-time transformation and transmission of the parameter like temperature, humidity, and CO2 directly into the digital twin environment, and have a way back, because we know that digital twin has to be bidirectional, because we have to synchronize the real data and then make some actuator to move and change something in the reality starting from the digital model. The connectivity is made by a REST API in this case. This is the creation of the first test that we made in the construction site. We can see some of the sensor, and then we tested the production, in this case of the concrete, to to take a look on the temperature, the humidity, and the CO2 that we create with the curing phase. The data integration is made also using Node-RED, that is a common orchestrator of sensor. You maybe can say that we can use a bazooka to kill a mosquito because it's a very easy test that we made, but we're thinking about the future. So we use Node-RED intentionally because it offers flexibility and also scalability from the beginning, adding maybe also a cybersecurity protocol that maybe in the future we have to check. In the future, with the smart mobile factories that became bigger with more sensor and also more pieces that we have to control, more activities, this is the setup allow nowadays a quick and structured implementation without redesigning all the entire system of the connection of the sensor. And this is the Unity environment in which we developed a dashboard that enable the real-time visualization of the sensor data. And one of the future objectives is to enable a real-time on-site, so maybe using MetaQuest or maybe a HoloLens, in which we can walk inside the factory and take a look like a small dashboard nearby the single asset and machinery, in which we can use to control maybe also the activities of operational and maintenance and something like that. Conclusion, so this paper and this test as a successful BIM-to-Digital twin integration using Unity and the REST API. We can transfer data through IFC format and preserve all the classification of the asset. And then we have a real-time visualization, and also we have, at the moment, manually decision and intervention from the BIM part inside the Unity to the real world. The limitation at the moment is that the actuator activities are not automated. We tested a limited number of sensors, and we tested also only the IFC format to pass the information in the Unity environment. There is no benchmark against existing BIM-to-Digital twin other methodologies. And then we have only a use cases that is the smart mobile factories cases, but for the future, I think we can use this type of approach for any kind of factories and building. Future direction, we have to automatize the control of the digital twin part for the reality. In the future, we have also one-to-one scale tank that we can use for testing in Dubendorf, so we'll be more focused on this part. We can expand all the sensor network. We can also explore additional BIM format for the Unity integration. We can also study the benchmarking of the state-of-the-art of other approaches and scenario. We can introduce more KPI, curing delay prevention, safety intervention frequency, system responsiveness, and then we can also have an evaluation of organizational readiness and the operational impact of the use of a digital twin to improve the quality and also the life cycle assessment of the production of the factories. Thank you for the attention. Thank you.